Welcome to my video. In this video, we are going to see about Multitask Catch Demonstrator. In this simulator, provides the capability to model a small-sized cache on a system that supports multitasking. In most of the modern processors today, it is often the case that multiple processes will need to share the resources of the system. Here we will simulate a cache on a system that supports multiple processes. The processes on the system must be scheduled in some fashion. We will explore some of these various scheduling methods later. The basic idea, however, is that generally we would like the process concurrently being run on the system to share the available resources. If the system only has one CPU, this means that process may have to yield the use of the CPU for another process. We call the operation of stopping one process and starting another a context switch. Since these processes are also sharing the cache of the system, it is possible that some of the blocks requested from this second process may be mapped to the same set in the cache as the previous process. If there are no more available slots in that set of one of the blocks from the previous process will have to be removed according to the replacement algorithm being used. At some point, however, the first process will be allowed to continue where it left off. However, the second process has left a footprint in the cache and has replaced some of the first process blocks. Now the first process must incur a penalty while it reloads the block it was utilizing before it was removed. We call this penalty the reload transient. We will now explore some of the options the simulator offers and how you can use the tool to simulate what we have discussed above. Configuring the simulator. The simulator provides many options that the user can set to mimic various systems and or scenarios. The cache content is treated as one word 4 per block after configuring the available options by pressing the Update Configuration button. The user can generate a series of memory accesses for each of the tasks by pressing the Generate Memory References button near the bottom of the table. A table displaying the memory references generated for each task will be displayed. The user can then press the Schedule Task button, and these series of memory access will be ordered scheduled according to the algorithm chosen in the Scheduling Mechanism option field. And finally, Step Run button can be used to show the state of the cache at various cycles. The cache will show which task and the corresponding block is currently occupying a slot, and you will also note that the memory references will be highlighted bold when a given miss was result of a reload transient. Directly under the cache is a series of hit, miss, reload transient cells that will change color based on whether these last cycle resulted in hit, miss or reload. Various statistics regarding the cache are displayed at the bottom of the page. Cache size. This option specifies the size of the cache in number of blocks. The cache size must be greater than or equal to the hashtags of sets in the cache. Hashtags of set. This option specifies the associativity of the cache or simplify the number of sets that the cache contains. The number of sets must be less than or equal to the cache size. Replacement policy. This option allows the ability to set the algorithm that will be used when a given cache block must be replaced due to a conflict. The LRU algorithm uses an aging method that will set the age of blocks in a set according to the time they were last accessed. The block that has not been accessed in the longest amount of time will be replaced. The FIFO algorithm will replace the block that was added to the set first. The RAN algorithm will replace a random block from the set. Scheduling mechanism. This option allows the ability to set the algorithm that will be used when scheduling the task and their corresponding memory request. It is assumed at time 0 that all of the generated memory requests are waiting to be received. A memory reference is assumed to use one's time slice. The FIFO scheduling mechanism will order the task and all their memory references in a sequential order, as it will be assumed that task A made its request first followed by task B. The round-robin scheduling algorithm attempts to distribute the processing time equitably among all processes. It will allow a given task to run until its time slice has expired, whereby the process will be preempted and the next task will be allowed to run for the same time slice. The priority based scheduling algorithm allows the user to assign a priority to each of the various tasks. The task with the highest priority will be scheduled first, but the round robin algorithm will be used in cases where two tasks have the same priority. CPU time slice specifies the amount of memory access a task can make before it must yield to another task. Note that this does not apply to the FIFO scheduling mechanism. Use random access sequence. Specifies that a random series of memory references should be made based. The other choice is to type in the block request for each task and each reference by hand. If this box is unchecked and you press the generate memory references button, you will notice that the typical table of tasks and their corresponding memory request is drawn. The boxes will be blank and should be all be filled in before proceeding. Locality probability. This option attempts to constrain the range of blocks requests that can be generated by each task and provide reasonable simulation to the principle of locality. The higher probability you choose, the greater the chance there is that a block that was previously requested by a given task will be requested again. Setting the value to 100% will result in the same address being used for all requested by the task. And similarly, setting the value to 0% will not constrain the randomness of the generated address in any way, with the expression that the simulation has been defined to limit the range of generated addresses to the 4x cat size in blocks. Hashtags of task. This option defines the number of tasks to be used for the simulation. Priority. This option allows the user to assign a priority to each task. The same priority may be assigned to multiple tasks. Allow more than 35 memory reference. This option must be set if you wish to set one or more of the task number of memory references option to a value higher than 35. The reason for this because depending on how fast your machine if you were run to a simulation with 26 tasks each of which made 99 memory references, then the simulation could take some time to complete. Number of memory references. This option allows you to define how many memory requests you would like each of the given task to be used in the simulation to make. You will note that the task name and its corresponding color that will be used throughout the simulation is displayed to the left. Clock options allows control over the number of cycles that are run upon each press of the step or run button. This option can be changed as many times as one wishes throughout the course of a simulation. That's all about the multitask catch demonstrator. Hope you all understood. Thank you.